Protocol-independent service queue isolation for multi-queue data centers. Abstract. To isolate the service queues in switch port, recent solution leverage the power of explicit congestion notification ECN. However, this caused a fundamental dependency on ECN-based transport protocol, making it hard to use generic transport protocols. To this end, we designed DynaQ, a protocol-independent multi-queue management solution that enables service queue isolation with generic transport protocols. DynaQ dynamically adjusts the packet dropping threshold of service queues. Our solution is inexpensive to implement on hardware through extensive testbed experiment and large-scale simulations. We showed that compared to alternative schemes, DynaQ is the only solution that achieves work-conserving, weighted fare sharing, and low latency without protocol dependency. Keyword service queue isolation, buffer management, data center network. Introduction. Data centers are shared by many services having diverse network performance requirements. To provide differentiated performance, the operation groups services into different traffic classes and maps the classes into service queues in a switch port 1 and 2. The switch enforces network policy across the queues through packet schedulers like strict priority queues (SPQ) and wait round robin (WR). Meanwhile, the port buffer is shared among service queues in the best effort manner. In this regime, it is difficult to isolate service queues because a queue with many flows can monopolize the buffer regardless of allocated size. If a queue cannot occupy enough buffer space, it cannot achieve its fair share rate as well. Recent solutions 1 to 3 leverage explicit congestion notification ECM, which maintains the maximum buffer occupancy around the ECM marking threshold K. Unfortunately, the existing solutions have fundamental dependency on ECN-based transport protocols. Since ECN requires the cooperation between end host and the switch, the protocol dependency is desirable because the end host cannot use generic transport protocols. The recent advances in transport protocols show that non-ECN protocols can outperform ECN-based protocol using different congestion signals. For example, in band network telemetry, fourths, credit, fifths, and network delay 6 and 7s. These works are motivated by the drawbacks of ECN like coarse-grained congestion, signaling, and slow converging time. Furthermore, in many multi-tenant environments, it is hard to enforce a specific transport protocol to virtual machines and bare metal servers because tenants own the network stack. In this context, we asked the following questions: how to isolate service queues in switch port without dependency on transport protocols. We answered the question by presenting DynaQ, a protocol-independent multi-queue management scheme. DynaQ enables services queue isolation with generic transport protocols. The vast import scheme and PQL provide us the following design guideline. First, to be work-conserving, a service queue should be able to occupy the buffer larger than or equal to the BDP. Second, to achieve weight fare sharing, the switch should guarantee the buffer as much as the weight BDP to a service queues. Third, to achieve the requirement simultaneously, the port buffer should be shared dynamically. Based on the guideline, DynaQ adjusts the packet dropping threshold of service queues dynamically so that a queue can occupy the buffer up to the port buffer size but does not take the buffer of unsatisfied active queues. DynaQ simply can be implemented on hardware inexpensively with up to 7 clock cycles. The overhead is relatively small because switch ASICs require at least 100 of cross cycles to process a packet. For example, Broadcom Trident 3 ASIC consumes at least 800 cross cycles to process a packet. We also discussed how DynaQ can be implemented on a programmable switching chip. As we implemented a software prototype of DynaQ as a Linux QDisk modules to compare DynaQ with various solutions. We built a small-scale testbed with 5 servers connected to a server-emulated switch supporting 8 times 1 GB port with 2 Intel i350 T4 NICs. We conducted extensive experiments to validate the efficiency of DynaQ. Our results show that DynaQ provides work-conserving weight fair sharing regardless of number of active queues, the number of competing flows, and different per queues waiting. Using multiple end hosts with different transport protocols, we show that DynaQ works well with generic protocols as well. In addition, DynaQ outperforms compared scheme in the FCT for small and large flows. To complement the testbed experiment, we also perform large-scale simulations using the NS2 with the link capacities of 10 GB and 100 Gbps. We demonstrate that DynaQ can preserve work-conserving weight fair sharing in high-speed data center networks. Per queue throughput, queue lengths, violate fair sharing by unfair buffer occupancy, background and motivation, impact of buffers on bandwidth sharing. Modern services have diverse network performance requirements. For example, web service requires low latency and data backup demand high throughput. To provide a differentiated network performance based on network policy, the operator often leverages multiple services queues in a switch port. In multiple queues environment, the operator classifies services into different traffic classes. These classes are mapped into different service queues, and the queues are scheduled by weighted fair package scheduler like WRR and then deficient round robin 1, 3, and 9. The operator also uses SPQ to prioritize latency sensitive flows. Second, shared SPQ queues have the higher priority and the other dedicated queues with fair schedulers have a low priority. Unfortunately, network policies can be violated in spite of packet scheduling. To saturate the weight bottleneck capacity, QIs requires the weight bandwidth relay product BDP, the WBDP-I, CRTT, where RTT is RTTC and WI denoted the link capacity and the weight of QSI, respectively. However, because the port for is shared among services queues in the best effort manner, a service queue may not obtain enough buffer as much as weighted BDP due to aggressive service queues. To show this, we conduct an experiment on small-scale testbed consisting of 5 servers connected to 1 Gbps. Each server emulated switching have of 85 kilobytes to buffer per foot. In the switch, we configure DRR with equal weight. We have 1 receiver and 4 senders. 3 senders are mapped into service queue 2, while the other senders belong to service queue 1. We start A flows from each of the senders at the same time and measure per queue throughput for 60 seconds every 0.5 seconds. We also record every queue length evolution and obtain 1K sequential samples and random time. Figure 1 shows the result. Since the queues have the same weight, bandwidth should be shared equally. However, Q1 cannot achieve its fair share rate because Q1 cannot occupy the buffer larger than WBPDP due to a large arrival rate of Q2. Why protocol dependency matters? The existing solution 1, 2, 3 leverage ECN to isolate the service queues. The solution have the underlying assumption. All end hosts use ECN-based transport protocols. This is because ECN requires both ECN-enabled end host and then switches. The assumption implies that the existing solutions have a dependency on ECN-based transport protocols. This is undesirable because the end host network stack cannot adapt to the advance in transport protocols. We have witnessed the emerging of many non-ECN transport protocols, which have better performance than ECN-based transport protocols. For example, HPCC force leverage in band networks telemetry available in emerging switches ASICs because ECN does not know exactly how to adjust the sending rate and caused a trade-off between latency and throughput with ECN marking threshold times. ExpressPath fibs shows that credit packets are better congestion signal than ECN in terms of fairness and convergence time. There also exist delay-based protocols like DX7s and Timely 6s, which are motivated by the ECN cannot inform the extent of congestion quickly. We believe that transport protocols will continue to evolve and their congestion signals will not be limited to ECN. The assumption also does not hold in many multi-tenant environments. Virtual machine and VM servers are the major component in multi-tenant data centers, and their network stacks is owned by tenant, not the network operator. Therefore, it is hard to enforce a specific transport protocols to all end host. Related work. Many wonder whether modify the scheme to drop package instead of ECN marking can solve the problem. However, we find that simple changes are not enough for the following reasons. MQECN determines a ECN marketing threshold of QIs as following the KI mean T round quantum C RTT times lambda, where quantum is weighted quantum of QI and lambda is coefficient for transport protocols. T round indicates the estimated total time to serve all queues at once. The key drawback of MQECN is that the solution relies on the concept of round with T round. This means that MQECN does not support packet schedulers like SPQ. Supporting SPQ is crucial to latency sensitive services since it accelerates small flows. Therefore, even we change the scheme to drop package, the solution does not achieve our design goals since it fails to provide low latency. TCN uses the packet surgeon time as the threshold metric instead of queue length. Since the packet surgeon time can be calculated after passing through the queue, the solution performs the queuing marking. The standard ECN marking threshold is given by T, RTT times lambda. If we change TCN to drop the packet when the packet surgeon time exceeds T, we should drop just DQ the packet. However, packet dropping at DQ causes idle time on the link. This seriously degrades the effective throughput. In addition, dropping the buffered packet increases the FCT as much as the packet surgeon time in addition to the retransmission time out. RTO, PSMB, third, provide both generic package schedulers and orange congestion notification, which MQECN and TCN do not support, respectively. PMSB only marks package when per port ECM marking and per queue ECM marking conditions are met at the same time, where the port ECM marking threshold is given by k equal CRTT times lambda. The per queue ECM marking threshold for qi is given by ki sigma w per wi c times rtt times lambda. Since ki, the dropping version of PMSB is similar to PQL, which is supported in some production switches. PQL assigns a static buffer size to a service queue. Therefore, each queue can enjoy its fair share regardless of other queues. However, PQL is not work conserving because the amount of buffer that the single queue can occupy is limited to a assigned queue quota. Therefore, when few queues are active, the link capacity can be underutilized since the aggregate buffer occupancy can be less than BDP. One might argue that assigning a buffer of the BDP to all services queues can solve the problem. Unfortunately, the on-chip SRM buffer is a scarce resource in switches 11s. Therefore, we do not have enough buffers to reserve a buffer size as much as BDP for all service queues. We also discuss shared buffer management solutions, like the dynamic threshold diagram. Many switches allow a single port to occupy many buffers. However, even if we allocated a large buffer size to a port, bandwidth cannot be shared fairly, since aggressive queues eventually filled up the buffer. It also harms per foot fairness by taking excessive buffers that can be assigned to the other port. Meanwhile, there exists deep buffer switches with the external large DRAM buffer. Unfortunately, the deep buffer switches have low switching throughput and insufficient per packet processing delay to satisfy the requirement of modern underfacing applications. Barber Q12 addresses a similar problem by packet eviction. Packet eviction is an effective technique to observe latency-sensitive microbursts. However, for service queue isolation, it is enough to use packet dropping. QPFabric 9 and QJump 13 also use multiple queues, but these works aim at minimizing the efficiency of small flows, not isolating service queues. Dynamic queue design goals. Our goal is to design a multiple queue management solution that enables service queue isolation in which it works over generic transport protocols. We stipulate that a good solution should satisfy the following requirements simultaneously. Protocol independence. A solution should not be tied to a specific transport protocols. Work conservation. A solution should be able to utilize the whole link capacity regardless any time. Weight fair sharing. A solution should strictly preserve weighted fair sharing among services queues any time regardless of traffic dynamics. Low latency. A solution should support arbitrary packet schedulers, especially SPQ, to minimize the efficiency of small flows. Practicality. A solution should be inexpensive to implement on hardware. Mechanisms. A basic idea. DynaQ is a first protocol independent multi-queue management scheme that specifies the above requirements simultaneously. We observed that the best of effort scheme and PQL provide the following design guideline that to utilize the bottleneck link capacity fully. A service queue must be able to occupy the buffer larger than or equal to the BDP if there is free space in port buffer to share bandwidth fairly while respecting different weight of service queues. A service queue must be able to occupy buffer space larger than or equal to weight BDP regardless of other service queues. To guarantee the weight fair share rate and sustain high link utilization at the same time, The switch should manage the port buffer dynamically among service queues. Without dynamic multi-queues management, we can meet only one of the two requirements at the time. Following the above design guideline, DynaQ allows a single service queues to occupy free buffer space in the port, but prevent the service queues from taking the buffer of unsatisfied active queues. Table 1 summarizes the mathematical notations used to describe our work. To realize the idea, DynaQ assigns a packet dropping threshold Ti for each service Qi, which means the total size of packets that can be buffered. The switch dynamically adjusts Ti every packet arrivals. Since a service queue should be able to occupy the buffer up to port buffer size, the switch does not simply drop the arriving packet P when the dropping threshold is exceeded. Instead, if the buffer occupancy of the service queue of packet P exceeded T with packet P, the switch increases the dropping threshold of the queue and decreases that of the victim queues, which is defined as queues has the largest extra buffer size. However, to guarantee the weight fair share rate, the switch drops packet P without threshold adjustment when the victim queues is unsatisfied active queues. Detailed design. DynaQ operates before enqueuing decisions. As shown in algorithm 1, the switch first compares dropping threshold Tp with the sum of the queue lengths of queue P and the size of packet P. In enqueuing, packet P does not make the queue length exceeded Tp, nothing will be done. Otherwise, the switch begins to adjust the packet dropping threshold or drop the packets. We express the Qi is unsatisfied if packet dropping threshold Ti of Qi less than satisfaction threshold Si, defined in EQ3, otherwise Qi is satisfied. Packet dropping threshold. DynaQ isolates service queues using dynamic packet dropping threshold. Each Qi has its own dropping threshold Ti. The aggregated dropping threshold of all services queues is equal to the port buffer size. If the aggregated threshold exceeded the port buffer size, the buffer will be shared like the best effort scheme. In contrast, if the aggregated threshold is less than port buffer size, the buffer sharing policy becomes close to PQL. Therefore, where the switch is on, DynaQ initializes the packet dropping threshold of Qi that Ti init equal P times sigma W Wi. In addition to ensure sigma I to M T equal P, DynaQ always decreases the dropping threshold of victim queues before increasing the dropping threshold of the queue of packet P. Victim queue selection. Because adjusting dropping threshold, the switch should find the victim queue buoys. One institution is that the victim should be queues who is expecting to experience the minimal impact after decreasing its dropping threshold. Therefore, a natural way to select the victim, finding the queue with the largest threshold. However, this may not work when service queue are with different queues weight. For example, consider 3 services queues with weight 1, 2, 3. The switch can choose Q3s as a victim queue, although Q3 has the minimum buffer size required to enjoy the weight fair share rate. To respect different queue weight, DynaQ selects a service queues with the largest extra buffer size as a victim queues. The extra buffer size Qi is defined as TIEX equal Ti minus Si. The satisfaction threshold Si specifies the minimum buffer size of Qi achieve its weight fair share rate regardless of the other queue. Theoretically, WBDPI is enough to saturate the weighted bottleneck link capacity, sigma W per Wi. However, we find that the switch does not preserve weighted fair share when SI WBDP. This is because TI fluctuate over time, preventing QI from enjoying its fair share rate stably. Therefore, we need to satisfy the inequality SI WBDP to make headroom to reduce the impact of the change of TI. Thus, we simply use the SI equal P times sigma WI. Modern line rate switches have enough buffer size allocated a buffer size per port larger than BDP. Since B over BDP, it is obvious that SI WBDPI. Victim queues search without loops. Finding the victim queue can be done through linear searching using loops. However, modern switching ASIC prevent loop operation to guarantee deterministic packet processing delay. To deal with this constraint, DynaQ uses binary search to find the victim queues. We make a max IDX function then return the index of the larger queue after comparing the extra buffer size between the two service queues. For example, when the switch supports 4 service queues, we can find the index of victim queues by referring to the return value of max IDX, IDX1, 2, IDX3, 4. This requires order log and complexity bounded to the number of services queues that the switches support. Modern switches typically support 4 or 8 service queues per port. Therefore, the complexity is fixed to order 2 or order 3, depending on the target switching architecture, packet dropping, and the threshold adjustment. After finding the victim queue, the switching decides whether to drop the packet or adjust the dropping threshold. The switch drops packet P is the dropping threshold of QV is less than the packet size of packet P, or QV is the unsatisfied active queues. The perform condition is to ensure TI upper 0. The latter condition is to protect unsatisfied active queues. If we allow a queue to take the buffer of unsatisfied active queues, a aggressive queue with many flows can occupy the port buffer excessively. Meanwhile, the switch does not protect inactive queues from the aggressive queues to utilize free buffer space for high link utilization. When the above conditions are not met, DynaQ exchanges the dropping threshold of queues V and QP as much as the size of packet P. This finishes the operation of DynaQ. After this, the switch performs packet enqueuing decisions based on the port buffer occupancy. 3. Discussion. We now discuss several design issues. ECN support. DynaQ should support ECN-based transport protocols, since they are also generic transport protocols. Since there exist ECN-based solutions, we employ PSMB rather than design our own ECN-based mechanism. Specifically, when ECN is enabled in the switch, DynaQ does not adjust dropping threshold but marks the package when the port buffer occupancy exceeds the port ECN marking threshold KC times RTT times lambda, and the queue length of arriving package queue exceeding the per queues ECN marking threshold KI WI W per WIC times RTT times lambda simultaneously. Port buffer size. We have assumed that port buffer size is constant so that the sum of dropping threshold sigma t can be equal to the port buffer size B. However, the operator can change the buffer size, breaking the equality between sigma t and b. This can be resolved by performing the initialization of the dropping threshold via equation 2 after adjusting the port buffer size. Implementation. Hardware implementation. DynaQ can be implemented on hardware inexpensively. Since we cannot program most switching chips, we first analyze the overhead in ASIC implementation. Next, we discuss the implementation of programmable switches, processing overhead in ASIC implementation. The processing overhead of DynaQ is ASIC implementation is relatively small since the switching ASIC consumes hundreds of clock cycles to process packet. Consider a typical hardware running at the clock frequency of 1 GHz where one clock cycle is 1 nanosecond. We also presume that the switch support A service queues per port. Note that commodity switch ASIC support 4 to 8 service queues. With algorithm 1, we can know that DynaQ requires up to 7 clock cycles. Broadcom tenant 3 ASIC offers a minimum per packet processing delay of 800 nanoseconds. For this case, the overhead of DynaQ is only 0.88%. Let us show the detailed analysis. In the worst case, line 1 to 3 and line 6 to 7 in algorithm 1, we performed line 1 consumes 1 clock cycle. Line 2 requires log A equals 3 clock cycles. Line 3 consumes 2 clock cycles because QV upper 0 and TV minus size P size SV must be performed before operation with TV size P. Note that comparison operations like QV can be pipelined. Line 6 to 7 require 1 clock cycle with a pipelining because they have no read-write dependency. Implementation of programmable switches. We analyzed how DynaQ can be implemented on the programmable switch built in with Barefoot Tofino. With Tofino ASIC, we can program processing pipelines. Our implementation is based on Tofino native architecture. TNA Tofino native architecture consists of 9 blocks, whose 6 blocks are programmable, and the other blocks only provide a fixed set of operations. DynaQ should be implemented in the packet buffer and the replication engine (PRE), where packet requiring and dequeuing decisions occur. However, the packet buffer replication engine is a fixed function block in TNA. Therefore, we cannot implement any packet buffering mechanism directly due to the limited programmability. We should implement DynaQ in either ingress or egress pipeline indirectly. Since DynaQ operates before buffering, we implement our solution in the progress pipeline. Most variables like packet dropping threshold, queue weight, and satisfaction threshold can be designed as user-defined metadata. In addition, we can manipulate them at runtime. Max IDX function to find the victim queues also can be defined in progress pipeline. All challenges to implement DynaQ TNA is to obtain the queue length information. Since the PRE is not programmable, it is not hard to obtain the queue length of the arriving packet queues in the ingress pipeline. Note that this is not an issue in ASIC implementation. In the TNA, the queue length metadata is included in egress intrinsic metadata, but it is prohibited to share metadata between the pipelines. Although TNA supports metadata bridging, we can only deliver in progress. implementation. In TNA, the queue length include in egress intrinsic metadata, but it is prohibited to share the metadata between the pipelines. Although TNA supports metadata bridging, we can only deliver in progress pipelining metadata egress pipeline. To deal with the issue, we may utilize an external register to inform the queue length to the ingress pipeline. We deliver the value of the DQ, queue depth metadata, the queue length at the packet DQ time. To the ingress pipeline, the value is stored in user-defined queue length metadata, and DynaQ reads it when the operation is triggered. This may result in DynaQ operations based on inaccurate queues length information. However, with round-robin based schedulers, we believe that some inaccuracy is tolerable to isolate service queues. The correct implementation of programmable switches is our future work. Sprayer implementation to compare DynaQ with various existing works in a flexible environment. We implement a software prototype of DynaQ as a Linux QDisk modules on server emulated switch. Our module consists of two stages as follows. In queuing stage, when the packet from TCP/IP stack arrives to QDisk layer, the module returns the index of the corresponding service queue by referring to the DSCP field in the IP header. Next, the switch checks whether the buffer is available to in-queue the arriving package. Basically, the switching performs packet in-queuing decisions based on the port buffer occupancy or per queue buffer occupancy relying on switch configuration. When the switch uses DynaQ, the switch performs additional operation to adjust packet dropping threshold before in-queuing. If the packet can be buffered, the switch in-queuing the packet into the corresponding queue. When ECN is enabled, the switch performs ECN marking at the end of the in-queuing stage. Dequeuing stage, the switching dequeuing package through work conserving packet schedulers, which include SPQ, DRR, and WRR. The packet schedulers follow the data structure and mechanism of the current Linux QDisk implementation. The dequeued packet goes to NIC drivers and NIC hardware before it is transmitted to the wire. Our module uses token bucket rate limiter to shape outgoing traffic at 99.5 of the NIC capacity. This is avoid excessive buffering in NIC drivers and NIC hardware, which can lead into inaccurate buffer occupancy in the QDisk. Performance evaluation. In this section, we evaluate the performance of DynaQ. We answer the following key questions. How does DynaQ perform in practice? Does DynaQ perform well in large-scale data centers? How robust is DynaQ to network settings? Traffic workload. We use 4 realistic workloads derived from production data centers, which are a web search workload, a dynamic data mining workload, a cache workloads, and a hard workload as shown in Figure 2. These workloads generate flows whose size distribution are heavily tailed. For example, in the data mining workload, roughly 50% of flows are 1 kilobyte, while 90% of bytes are from flows larger than 100 megabytes, like MQECN and TCN2. We also used a web search workload for all services queues in the test-based experiment, while using all the 4 workloads in simulations. This is because the web search workload is the most challenging workload due to its less skewed flow size distribution that generates multiple concurrent flows on the bottlenecks. In addition, it is hard to make all workloads active during experiment because every workload results in different finish times. Compared scheme, we mainly compare DynaQ with the following schemes: best effort and PQR. Best effort denoted the best effort scheme that manages the buffer among service queue in FINO manner. PQR isolates service queues by reserving a static per queue buffer size. When you consider low latency, we also compare DynaQ against the DCN-based solutions, DCN2 and PMSB. Performatory. Our primary performance metrics are throughput and FCT. We also use throughput share ratio and Jane's fairness index for better understanding of throughput result. For the average FCT, we break down the FCT across different flow sizes to analyze the impact on small 100 kilobyte and large flows 10 megabyte. We also consider the 99 percentile FCT of small flows to evaluate the tail latency. Due to space limitation, we omit the result of medium flows whose results are similar to the overall flows. For clear comparison, the FCT results are normalized by the values of DynaQ. Testbed experiment. Testbed setup. We have to build a small-scale testbed which consists of 5 servers connected to server-emulated switch. The switch is equipped with two Intel i350 T4 V4 NIC, where each NIC supports 4.1 gigabps port. Each server is also equipped with the Intel Gigabyte NIC. All servers use Linux kernel 3.18.11. We use TCP for the non-ECN schemes and DHCP for the ECN-based schemes. We set TCP RTOs to 10 milliseconds as suggested in many existing words 1 to 14, 17, 18. The initial congestion window size is set to 10 packets as suggested in RFC 6928. In end host and switch, we desirable large send offload LSO and large receive offload LRO to reduce the traffic burstiness and emulate switch hardware behaviors more correctly. To emulate a switch with Broadcom 56538 ASIC, the switch has 85 kilobyte of port buffer, which is completely shared by all service queues. PQR is the only exceptional scheme since it limits per queue buffer size. The base RTT is roughly 500 microseconds, and the corresponding BDP is 62.5 kilobyte. We set ECM marking threshold for TCP, TCP/TCP and TCN to 30 kilobytes and 240 microseconds, respectively. These are the best values experimentally found. Note that there is theory practical gap determining ECN marking threshold. Static flow experiment. In static flow experiment, we focus on weighted fare sharing and work conservation, convergence, and queue evolution. In this experiment, we show the Bayesian result with two active queues between 4 DLR queues having the equal quantum of 1.5 kilobyte. We use 3 servers, where 2 servers are the senders for each service queues and the other one is a receiver. Using iPerf, each sender starts flows to the receiver for 10 seconds. The second of queues to generate 60 flows, while the sender of Q1 has only 2 flows. Ideally, the active queues should share bandwidth equally regardless of the number of competing flows and the inactive queues. Figure 3 shows throughput of the active queues over time. It is easy to find that DynaQ is the only solution the shared bandwidth fairly. Throughput of the active queues is the best if all does not converge, resulting in significant unfairness with PQL. The active queues share the bandwidth fairer than best of effort, but still result in considerable unfairness. Figure 4 reports the queue length evolution for the active queues. We measure per queue buffer occupancy every in queuing and dequeuing operations and obtaining 1K. First K sequential samples. The dotted lines indicate per queue buffer size. The queue evolution samples explain the throughput in figure 3. The best effort since Q2 has more flows. Q2 dominates the port buffer while Q1 with similar flows occupies a smaller buffer. In PQL, Q2 can occupy buffer space more than that in best effort, but it is limited to reserve size. Unlike the other schemes, DynaQ shares the buffer dynamically that dropping threshold change over time. Thanks to this, each queue can occupy enough buffer regardless of number of flows and active queues. Weighted fair sharing and work conservation. In this experiment, we consider 4 DRR queues with equal quantum as same as previous experiment. However, we now vary the number of active queues over time. Each queue has different number of flows that the sender of queues I starts to I flows to the receiver simultaneously. From 10 seconds, we change the number of active queues by stopping flows. At 10 seconds, the sender of Q4 stops traffic. After 5 seconds, Q3 becomes inactive. At 20 seconds, the sender of the Q2 no longer send flows. The sender of Q1 finishes at 25 seconds. We measure per queue throughput every 0.5 seconds and obtain aggregate throughput as well. Ideally, service queues should share bandwidth fairly regardless of number of flows, and the aggregate throughput always should be high regardless of the number of active queues. Figure 5 shows the result. We observe the best effort fails to achieve fair sharing. When all the 4 queues are active, Q4 with 60 flows occupies the largest bandwidth share because the port buffer is dominated by packets of Q4. Due to this, Q1 only obtains 0.14 gigabps of average throughput for the first 10 seconds, even when only Q1 and 2 are actively at 50 seconds. The queue do not share bandwidth fairly in spite of scheduler because Q2 has twice as many flows as Q1. PQL shows the better result than best effort when all queues are active. PQL preserves fair sharing. However, when the number of active queues decreases, fair sharing is violated. We can see the unfair bandwidth sharing between the two services queues, 50 to 20 seconds. More importantly, we can see that the aggregate throughput decreases as queues becomes inactive. It is notable that the average aggregate throughput during 20 to 25 seconds is only 0.78 gigabytes. This is because each service queue cannot utilize the remaining free buffer space. Unlike the compared scheme, DynaQ makes the service queues share bandwidth almost perfectly regardless of the number of flows. In addition, since DynaQ also allows a queue to utilize free buffer space, the aggregate throughput does not decrease even when few queues are active. Impact of queue weight. In the experiment, we use the same scenario in the previous experiment. The difference is that we configure different quantums for the DRI queues. Our default quantum is 1.5 kilobyte of MTU. We set the weight of the queues of 4321, which results in 6 For the 531.5 kilobyte quantums, we measure the per queue throughput average 0.5 seconds for 10 seconds. Ideally, the queues should share the bandwidth by respecting their assigned weight. Figure 6 shows the throughput share of each service queue. The throughput share is defined as RIT, sigma RT, where RIT denotes the throughput of the QI at the time t. The result of the best effort shows that best effort does not preserve weight fair sharing. In spite of different quantums, best effort allows a queue with many flows to occupy more throughput share. For example, the average throughput share of Q4 for 10 seconds is 0.35, although its desirable share is 0.1. PQ achieves a weighted fair sharing in this experiment. This is not surprising because PQ assigns a static buffer size to each service queues. However, as we have shown in the previous experiment, PQ less throughput as the number of active queues decreases, although it is omitted in this experiment. The result demonstrates that DynaQ achieve weight fair sharing by respecting the assigned weight regardless of the number of competing flows. Impacting transport protocols. We consider a scenario where senders use different transport protocols. We have tried to use emerging protocols, but it is hard to obtain their codes. Instead, we use TCP and cubic. Unlike the previous experiment where all senders use TCP, we now make the senders Q3 and Q4 use cubics. Except the transport protocols, we use the same scenarios in the equal sharing experiment. Figure 7 shows the result. We can see that DynaQ achieves fair sharing regardless of employed transport protocols. One notable point is that at 10 seconds and 15 seconds, we can see that the aggregated throughput decreases slightly for amount when Q4 and Q3 become inactive. This is because of the time for ramp up of the other queues, not due to our buffer sharing policy. Dynamic flow experiment. If dynamic flow experiment, we shows that DynaQ can achieve low latency. Methodology. At the switch, we configure SPQ DRR where one queue has higher priority than the other 4 DRR queues. Packets in the DRR queues can be dequeued only when the SPQ queues is empty. This is a common switch configuration to accelerate the latency-sensitive small flows. Second, we use 1.5 kilobyte of equal quantum for all DRR queues. We use client-server application generate traffic with a web search workload. We have 4 servers and 1 client. The client initially opens 5 persistent TCP connections to each server. The client generates requests to server through available connections. When there is no available connection, the client creates a new connection. The inter-arrival time of generated requests follows a poison process. When a request arrives, each of servers responds with a request data size. The server application sets DSCP values for outgoing packets using SESOpt, and flow mapped is one of the service queues randomly. We also employed 2 levels of PIAS to classify small flows with 1000 kilobyte of priority demotion threshold. Therefore, the first 100 kilobytes are buffered into the SPQ queues, and the remaining bytes are enqueued into the DRR queues in the low priority. Overall, we generate 10 kilobyte flows by varying the traffic load from 30% to 80%. Comparison with non-ECN schemes. Figure 8 reports the FCT result that compare DynaQ with non-ECN schemes. The average FCT of all overall and large flows are similar since most of bytes in the benchmark traffic come from large flows. Compared to PQL, DynaQ achieves the better average FCT for large flows by up to 1.95 times. Similarly, DynaQ outperforms PQL in the average FCT for overall flows by up to 1.80 times. This is because service queue in PQL can occupy limited buffer space. The result against the base offer are mixed whose gaps are within 0.90 speed, 1.02 and 0.80% to 0.97 for the average FCT over flows and large flows, respectively. The reason why best effort outperforms DynaQ than large flows blocks small flows in the port buffer. Not surprisingly, we can see that DynaQ significantly outperforms best effort in the FCT of small flows. Although best effort outperforms DynaQ in the FCT of large flows, best effort cannot preserve weighted fair sharing as we have shown. For the average FCT of small flows, DynaQ achieves the best performance between the schemes. DynaQ beats best effort by 1.26 on average across the traffic nodes. The performance gap increased as traffic load grows. Compared to PQL, DynaQ has a better performance within 1.08 to 1.14 from the 99% of FCT result. We find that best effort show a significantly worse performance than DynaQ when traffic load increases. For example, the FCT gap in 60% of load is 0.40. Unlike best effort, PQL shows relatively stable performance. However, DynaQ still outperforms PQL by 1.14 on average across the road. Comparison with the ECN-based schemes. We now discuss the FCT result of DynaQ compared to the ECN-based schemes. Figure 9 shows the result. Like the result in Figure A, the result of the overall large flows in the similar. DynaQ shows the mixed performance against the based solutions, but generally outperforms the comparisons. TCN shows the similar average FCT for overall large flows when traffic loads within 30 to 40%. However, the maximum gap is only 0.95 times for overall flows when load is 30%. DynaQ outperforms TCN for the rest traffic loads, whose the range of performance gaps are within 1.28 to 1.85 and 1.29 to 1.99 for overall large flows, respectively. PMSB also has similar performance to TCN. Per Q, ECN shows the worst performance between the schemes. When we consider the result for small flows, DynaQ beats the other ECN-based schemes in both average and 99% percentile FCTs. For example, DynaQ is better than PMSB by up to 1.29 times in the average FCT. The ECN-based schemes show the worst performance and lower traffic loads than high traffic loads. DynaQ performs PMSB and PartQ ECN by 12.23 times and 12.63 at 30% of the traffic load, respectively. Large-scale simulations. We conduct simulation to evaluate the performance of DynaQ in large-scale environment using NS2. Static flow simulations. In the simulations, we evaluate the DynaQ robustness. methodology. Likely test mode, we build a star topology to emulate computer lag. We consider two high-speed links, one 10 GB and 100 Gbps. The base RTT are 84 microseconds and 40 microseconds for each of links. In the switch, we configure WRR with equal weight for packet scheduling. We have enabled jump frame for 100 Gbps links. We consider Broadcom Trident Plus and Trident 3 ASIC for 10 Gbps and then 100 Gbps links, respectively. Therefore, each port has 192 KB and 1 MB of buffers, which are completely shared by service queues, except in PQL we use TCP for the transport protocols and the RTO minimum to 5 milliseconds. The lowest stable value in Jiffy timer, impact over link capacity. We first perform simulation with 110 Gbps links. We have 8 services which are mapped to each of the 8 service queues. There exist two types of I senders. For QI, every sender of services queues starts a flow at the beginning of simultaneously from 200 Mbps millisecond. The senders of queues 2 to A stop their transmission every 80 milliseconds in order. For example, the senders of queues 3 finishes its flows at 250 milliseconds at queues 1, the only active queues after 500 milliseconds. We measure per queue throughput every 10 milliseconds. Using the measures data, we calculate James fairness index between active queues and the aggregate throughput. The aggregate throughput is the inspect whether the links is fully utilized at any time. If a solution preserves weight, fair, sharing, and work conservation, the two metrics always should be high. Figure 10 shows the bandwidth sharing result with 10 Gbps links. Not surprisingly, DynaQ and PQL achieve the near optimal fairness index, while best effort causes fluctuations. For example, the fairness index plunges to 0.67 at 410 milliseconds. This is because best effort cannot handle service queues with many flows. Figure 10b shows that DynaQ is the only solution that maintains high risk utilization between the schemes. When QA finishes at 500 milliseconds, PQL causes a huge throughput collapse. PQL maintains the aggregate throughput around the 0.5 Gbps after 500 milliseconds. This is because Q1, the only active service queue, cannot occupy the buffer as much as BDP. We performed the same simulation with 100 Gbps and figure 11 reports the result. We find that DynaQ can achieve work conservation and preserve weight fair sharing with a high link capacity. The overall tendency is very similar to 100 Gbps result. Best effort cannot provide per queue fairness, and PQL loses a significant amount of throughput when service queues 1 is the only active queue. In addition, DynaQ does not lose throughput much at 500 milliseconds. Unlike DynaQ, best effort causes 0.9.2 Gbps throughput losses. Impact on traffic dynamics. We now impact how DynaQ robust traffic dynamics. We conduct a simulation with almost the same scenario as the previous simulation with 1000 Gbps. The only different setting is the number of senders per service queues. We consider a very extreme scenario where service queue I has 3 plus I senders, generating a single flow. For example, Q8 has 2048 flows. Figure 12 flows the result. We observe the DynaQ is robust to extreme traffic scenario. Best effort shows the worst performance in the fairness index, then it achieved only 0.24 of fairness index for the first 200 milliseconds. The scheme also lost throughput 300 milliseconds for a moment. PQR still fails to achieve work conservation. The aggregate throughput stays below 94.5 gigabps from 500 milliseconds. Dynamic flow simulations. We now evaluate DynaQ performance in large-scale data center networks. Methodology. We build a non-blocking leaf spine topology, a wide-use data center network topology design. Our topology has 12 leaf TOR switches and 12 spines core switches. Each leaf switches has 12 to 10 gigabytes downlink and 12 times 10 gigabps uplinks. The best RTT across spine switches is 85.2 microseconds. We use ECMP as a load balancing scheme. We use TCP and RTO minimum is 5 milliseconds. Each switch port has 192 kilobyte buffer shared by service queues except in PQR. We configure SPQ DLR with a service queues where one queue is shared high priority queues and the other 7 queues are dedicated DLR queues with equal quantums. Like the testbed experiment. We also employ a two-level PIAS whose priority demotion threshold is 100 kilobytes to classify small flows from large flows. We even classify the 144 times 143 communication pairs into 7 services, and each service has its own service queues. Different services use different traffic distribution in Figure 2. We generate 10 kilobyte flows by varying traffic load from 30% to 80%. Result. Figure 13 shows the result. Due to space limitation, we only discuss the average efficiency of overall flows and the 99% percentile efficiency of small flows. In the average efficiency for overall flows, we observe that DynaQ has mixed result compared to best effort and outperform PQRs. This is similar to the result in the testbed experiment. The gaps with the best effort are within 0.98 to 1.01 for the 99% efficiency of small flows. We can see that DynaQ achieves similar performance to the pairs schemes. PQR slightly outperforms DynaQ. The maximum gap is 0.98 in the testbed experiment with 1 gigabps links. Best effort result in a performance degradation when loads are high. However, with 10 gigabyte links, DynaQ beats best effort only by up to 1.01 due to the increased link capacity. Conclusion. This paper proposes DynaQ multi-queue management solution for multi-queue data centers. DynaQ is the first protocol-independent solution that can isolate service queues with generic transport protocols through dynamic packet dropping threshold. We have discussed how DynaQ can be implemented on hardware. To compare DynaQ with existing solutions, we have implemented a software prototype DynaQ as Linux QDisk modules. We conducted a series of testbed experiments and simulations. Our evaluation results demonstrate that DynaQ ensures work conservation, weighted fair sharing, and low latency without protocol dependency.